तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have seen how to design Verilog codes for combinational and sequential circuits, and what we have done is we have seen only piecemeal codes as such. It is not a full-fledged code. Now the present attempt is to make it full-fledged so that it is suitable for platforms such as simulation and synthesis and so on, and we will call it by the name coding organization, because there are more statements to mere assign always and the like of it, which we have already seen earlier. And to start with, let us assume that your design is a module like this, just a block. You can regard it as a black box to start with, and depending upon what functions you are going to integrate in your design, you can give a meaningful name to that. Say, let us say we call it module name, underscore is only to make the readability better, and this particular module will naturally have some inputs and outputs, and these are all listed right here. We have already seen reset, clock, and in addition to that we will have just 3 inputs for sake of making it clear to you, and this also has 2 outputs as such, and they are all out 0 and out 1, and you can call this your design module or simply the module. And now how to code this in Verilog? So what you see is you start with write on your paper with this block and then go on to code it, and the way to code is right here. See, first we said module name, and that is what appears here, and before that we had to say it is a module, and naturally the whole thing is identified by this module name, which is particular to your design as such. And what is this is a keyword in Verilog to identify there is a module here. So there will be a module here and a corresponding end module at the end, which we will see towards the end of this piece. And here note that there is a bracket here, it starts there and ends here, and followed by a semicolon. and don't forget the semicolon or the braces mentioned here. And you have already seen this line comment. So you can freely use the line comments just to explain what you are doing in any part of the design. And here what you see is a list of the same IOs that we have already seen in this block earlier. So these things plus the outputs. In fact, all the IOs stands for inputs and outputs. So are listed here, and notice that each one is separated by a comma. And also notice the last one is there is no comma for the last one. And if you violate any of this, naturally the compiler will complain, right? And so what you had to first, after this you had to declare first inputs and outputs. You have not mentioned here what you have not identified the actual inputs and outputs here. So you had to do the identification, which is a logical sequence here. And after this, all these have been put in comments just for your clarity's sake. And this is not a full-fledged program as some code as such. And next item is registers and wire. What they are we'll see after a few minutes, and they are basically signals used in always block for registers, and assign statements etc. will be wire or net. We'll go into little more details little later. And then you follow with your actual code. And what we have already covered earlier in combinational and sequential circuits were precisely belonging to this category as such. And finally, as I said, wherever there is a module, there must be an end module. So in summary, you have nothing more than module and then module name, then followed by IOs, and then your declaration of inputs outputs, and then as well as registers wires, then your actual circuit here, and then finally don't forget to put an end module. Note that there is no gap here after end. Here starts the actual code. Now we have already seen in C we use this symbol for slash star here, and a matching star slash at the end of the comments. It is more than one line, you can use this as in C. And what we are going to do is realize a combination circuit using Verilog codes. So we have already seen these comments as such. We had to declare a module name, and then what is new here now is whatever you have as a module your design, you will have to ultimately put it into a file, and when you make it into a file, give the very same name that you have had earlier. For example, module name was the name of the module that you have given for your design. So make it a habit to use the very same notation even for saving it as a file. For example, the file, I wonder whether you can read it here. I will just read it for you. It simply means com_circuits.v. So don't forget the extension .v to indicate that it is a Verilog and not VHDL. In VHDL you say VHD as such. So .v is the extension that you have to give for any meaningful name that you have here. And once again I repeat that com circuits is nothing other than your module name, and the file name should match with that. You cannot nest multiple modules. In fact, I mentioned this earlier lecture also. If you have different modules, you have to put it in different files as such, and call those modules here, and what we refer it to as an instantiation as such. So we will go into depths of those later on. When the design gets more and more complicated, you have to resort to such methods. And for simplicity's sake, I have put all those that we have learnt in combinational and sequential in just two files as such, and named appropriately for sequential circuits for the other one. So here we have already seen that this is the end of this comment here, more than a line, and that's what is mentioned here. So it this means a line comment as such. Now taking the model we have already put there, for instead of here we have used I think module name. So now we replace that by com circuits, because our intention is to put all the combinational circuits that we have learnt earlier and into one file as such. And once again we see there is a module here, and the code might be a long thing. So, you normally tend to forget an end module towards the end. If you forget, it will the compiler will tell you, and initial for beginners it may be difficult. So, a good practice would be to put module and straight away end module and keep on keying in between things so that you will not forget. And once again we have braces here. There will be a start here and there will be an end brace at the toward the end, and we will have to declare all the IOs here. And which order you mention is left to you. Whatever is convenient to you, you can do. It is rather a free format in Verilog as such. And ABC can be an output, or one can be an input or output, or output and input. Any combination that you prefer you can have. So, it all depends upon your practice as such, right. And whatever you practice, start you have made, stick on to that, so that it is readable for you, not only for yourselves later on after years of usage and you want to revise the design, but also for others who will be using your codes as such. And we have already seen here, we had to declare the design module as such. That is what is being done here. This is the module name that we give, and that is how we declare here. And what appears here, A, B, C, I naught and so on, note that every input is followed by a comma as such, just to indicate that this is one signal, another signal is this, just a comma separates one signal from the other. And another thing, I wonder whether I mentioned it to you earlier, why is this style adopted? I will explain. This again depends upon the designer to designer. I prefer this style, and the reason is we can easily spot out where a particular signal has been used or not used by mistake. So, if you club all of them in a single line, which you can do, it will be difficult to track. Of course, there are in editors there are such, but this will be an easier thing. So, I leave it to your taste as such to handle it. There is no restriction regarding that. And these are all the inputs that you have already seen in the codes earlier, and I may not go into the depths of the codes again, but I will do so while during this simulation period, and that will avoid unnecessary repetition. So, I may not explain today the actual code which we have already covered. And you can see all these are basically inputs here, which we will have to define later on. And some of them are single bit, and others are multi bit as such, and these are all the outputs. So, right up to F11, F12, and here the comment says here, note that these IOs are separated by commas, which you have already seen, except the last. This also I think I have mentioned earlier, and so it's a quite a it's a pretty long list of IOs here. All the outputs. Oh, yeah, you are right. So, there must be a comma here. So, the compiler will compile here, right. And in fact, the compiler will not really throw full light on that. It may start complaining for whatever follows later on also, that also may be there, but here in this case it may not. Okay, what we have done is just a listing of the IOs, but we will have to identify which particular signals are inputs. So, that is what is being done here. So, for example, A, B, C are all inputs here. So, here just put a comment saying that we declare all the IOs here. And coming to this statement, you notice that N1 is an 8-bit number, which we have already covered, and we will touch upon it when we go to the actual assign statements that also that will follow suit here. And MSB, as I mentioned, is 7, and that is the first thing that should be put here, right. This is a prerequisite here, right. If you interchange, there will be lots of confusion. It will interpret as MSB, so you will have lots of problems. So, stick on to this, and this as usual is N1 is the input. And the only difference is you do not for 1 bit, there is no point in putting 0 there, right. You can dispense with it. So, but that is what is implied here. So, here you put 7 to 0 for the 8 bits, and the same inputs continue for different dimensions, different signals. This is 9 bits here, and these are all 1 bit output here. Just as you declare an input, you can also declare output and once again list. And as I mentioned earlier, you don't have to first list all the inputs and then go to outputs. If you feel like, you can say one input, one output in any mix that you want. Once again, here you can see multi-bit represented in a similar fashion.
Outputs and inputs also come as groups instead of one line.
No, it can be groups or it can be a twisted jumble of this.
No.
Yeah.
One line for each you have done your style.
Yeah, that's.
It can also be grouped together.
Yes, it can. See, a semicolon actually separates one statement with another.
But I don't understand output again if you put in the same line. Is that right?
Yeah, you can just put comma F11 and so on.
Yes.
But readability suffers. That's the yes. And once again, we had 2 input mux that outputs. You have a listing here. 2 input, 4 input, and 8 input mux. And once again, they are all single bit. And we also had a demux. That output is D0 through D7. And once again, output multi-bit used in different places. For example, we had done a full adder. We have seen behavioral, structural, etc. All those things are put here. Only difference between the coding explained earlier and here is I might have used the very same nomenclature. But when you start putting it as a code, full-fledged code as such, you have to have different names, otherwise the same signal will be overwritten. That's the reason why I had made very slight changes, just rename it, nothing more. And similarly, all outputs up to F18 and so on. Once again, it's precisely the same what you have seen. So I'll just go to the next. See here, we have used assign statements earlier and assigned some outputs. So whatever output appears in assign statements, they will be wire as such. What is a wire? For example, you have a combination circuit, the output of which can be declared as a wire. It is something like physical wire that you have in your circuitry, which you had used earlier, and in schematic circuit diagram also you refer that as a wire, or in some cases as a net as such, right. For example, a microprocessor bus signal, any signal that you want to have, you can treat that as a wire as such. It's a physical wire connection, that's why they have retained this name wire. And once again you see multi-bit represented in similar fashion, and followed by the actual signal name. And these signals may be an output straight away appearing at the output of your design module, or it can be intermediate outputs as such, used in subsequent sequential circuits, etc. And so is the case for other variables. And this is an output. These are all, these are all intermediate outputs, which we will see when we go to the code as such. And that's what we have said here. Declare a net as such. Net is declared as wire as such. Then comes your always blocks, whether it is combinational or sequential. In sequential you have a positive edge clock, so always at positive edge clock. In ordinary combination circuit you have always at when select or I0, I1, all inputs you list. Whenever there is a change, only then that will be processed. So whether it is, any always block for that matter, you declare those outputs that you have mentioned therein as a register. So this is another easy rule to remember. So for assign statements you can say wire, and for always block whatever output, all are with reference to the outputs only, not the inputs as such. And you can refer to as a reg in always block, whatever signals that come in that. Once again you see here for reg multi-bit, it is through this. And for single bit we have Earlier we have used D0 through D6 in an always block, if you remember, and therefore they are declared as reg here. So this mandatory thing, you have to declare any signal that you use either as a wire or reg, and even outputs would be normally a reg if it is coming from the sequential circuit. And once again, you see, these are all we didn't use always block, we used assign statement for this. So we use a wire here, and we used an always block for mux site, therefore it is a reg. And these are all in always positive edge. In sequential circuits, I think we have used this, that's why we have declared as reg. Once again, a multi-bit here, and we made a small design block which compute this sum and then reports whether a match has been found with a preset value, and those outputs are all this. This is a multi-bit 9-bit output, and these are all single bit, and hence this, and all were in the sequential block, therefore it is I am not sure whether it was sequential, we will have a look when we come to that. So to start with, we had covered earlier this, right. We said how to implement a buffer using an assign statement. Precisely that's what we have put here in the the statements appear here. So up to that. So that's what is appearing here as it is. That's why we said before that we will deal only with the core of the statements first, so that you get a quick grasp of those fundas, and then go on to more details which we have already seen here, that is namely identification of module, and then how to put it together, then IOs, and then declaration of wire and reg, right. And so you can put once again a meaningful comment here, and I will not go into these details. Perhaps to just recollect, this is an ANDing operation, this is an OR operation, this is a NOT operation, and you can have an AND etc. by the combination of this, that is what is listed here, and for exclusive OR you can use this symbol hat. So we have also seen using always block different combinations circuits. For example, we realize this majority logic, which is AB plus BC plus CA, and this is precisely what we have already seen here in one of this. Okay, this is pictorially depicted here, you have already seen this, and next example was concatenation of 3 signals ABC, and this will be the MSB, which we have already seen. So these are all the inputs to this thing. What it does is puts them together in this order, and you can regard that F10 as one signal which has 3 bits, A being the MSB. And that is what we have put here in this statement, and you give once again a meaningful comment. And then we saw shift registers shifted by 1 bit and 2 bits here, and this pictorially depicted. You start with F10, and when you right shift by 1 bit, this is how it happens, and 0 is filled in the vacated bit position, and if it is left shift, the other way happens. And now in this case 2 zeros are filled because you are doing 2-bit shift here, and what is shifted, these things are lost unless you store it deliberately, and that is what we have here, these 2 statements. And then we have seen how to model a multiplexer. We can use an assign statement, and this is a 2-input mux, and with A is a selector control. If A is 1, I1 is routed to mux 2, otherwise I0 is taken as mux 2. Mux 2 is the output as such. And similarly, we have seen a nesting of 2 such, this basically a mux, a question mark, and you have a nesting of 2 muxes here, and in order to deal with 4 inputs as such, this also are explained, and B and C are the select pins as such, B being the MSB, and that is what you see here in these 2. that is for the first 2 input mux, and then followed by 4 input mux pictorially depicted. And then we have also seen an 8 input mux. So, I0 through I7 are the inputs, and mux 8 is the output, and selector pin ABC MSB is A, and this is important as such. And this we have also mentioned that this results in the fastest possible hardware implementation as such. And we have also said that always block has been used, and whatever outputs that you have, that must have been declared as reg earlier. You can go back and find out whether mux 8 has been declared as a reg, whereas mux 2 and mux 4 were declared as a wire as such, because they do not appear in this always block. And we list all the inputs, and whenever there is a change of input, only then this case statement will be processed. Case has concatenation of 3 numbers, what we have already seen earlier, and if ABC is 0 0 0 respectively, then I0 is selected and output to the mux 8 signal, otherwise other signals are output. This also we have seen in depth. So, the last one is say 111 corresponds to I7, and you may encounter X, that is don't cares, or tri-state say Z, and in such cases you have to account for such cases as well. So, that is why we put a default here. So, it is a good practice to have a default and take it to a safe state as such. It might be you may according to your circuit design, you may consider 0 as a safe state, in some other condition 1 or X or Z, depending upon your real need. You can just initialize to some safe condition as such. And once we had a case, we need to have an end case to complete the thing, and we started after always one begin. So, end is there here, and notice that there is no semicolon either here or here. Now, what we are doing here is we have got using 8 input mux, 8 outputs, one output as such. That output will feed it to another demux. It is a reverse process, and see whether what we started with inputs for the mux appears at the output or not. That will be easy to check while doing the simulation. That is why I fed it back like this. So, in this case once again you use an always block and a case, and these are all exactly the same meaning as before, and only difference is note that when this combination is met, mux 8 is output to D0, and this pictorially is this. So, what we have done here is mux 8 was the output of earlier mux here, we feed it back. So, you expect at D0 through D7 precisely what you have fed at the input here, and once again this has the same meaning as such. This is a demux, or you can even say a decoder, right. And here coming to that, only this is applicable. So, what happens to the other outputs? You have to force them to 0. If you do not, you may land up in a problem later on, because it might have come from earlier state with 1. So, it latches on to that condition if you do not mention. This also we have seen while dealing with RTL coding guidelines as such. And similarly for other cases, all the 8 cases are considered here, and in each case you see that mux 8 is assigned to the corresponding thing. This 4 corresponds to this 4, although it need not necessarily be. And another point I may mention is, you have put everything in a sequential order, say a binary sequence. There is no need for you to do, and also this may be painful to write so many bits. If you have 64 inputs, you will have to write very many, and more the number more you had to write. So, better thing would be to use a decimal here. You can just replace this B with D, but even in that case this will mean only number of bits. So, you have to take the trouble of computing first how many bits it will run into maximum, then put this. So, this tick is a prerequisite here, and this colon is also a prerequisite here, and we have once again covered a default here, right, and we have taken all of them to 0 state, and once again end case, end matching end, and then we have seen a full adder as such. We have seen three types of full adders. So, one is a behavioral level. This is the best because you need to write just plain addition symbol as such. So, you all of them are 1 bit, and you add A and B. There is a bracket I have explained earlier also. Guide the synthesis tool because it cannot make a decision all by itself what you intend doing. So, you had to tell the synthesis tool, then do this in parallel with this. That means to say, when here it is redundant. If you had one more here C plus D, you can put another parenthesis, then C plus D and A plus B will be done simultaneously. And we have also seen earlier while in RTL coding precisely that example. And there is the same end result can be achieved in two other ways. Another way is what is called the data flow realization, in which case you straight away deal with the actual get, but in a concise manner as this. So, you know that this is nothing but exclusive ORing of 3 inputs. So, we do this here. Once again, to get the synthesis tool, you put this. That is what the sum was. And then here a carry was nothing but majority logic, which we have already realized earlier. And notice that as an example, in order to show all these features, I have interconnected them, using namely to use the very same inputs, outputs as far as possible, right. So, only thing outputs have been changed, as I mentioned before, because two results will be contradictory. So, it will take the latest and it will overwrite the previous result. So, that is why name has been changed in some cases, and in fact this carry etc. I had used very same name. Now, I have marked difference here. See, I have just extended carry out underscore df. It is to connect it data flow, because that is what we are dealing here. And data flow is very much akin to your RTL coding, although RTL coding has graduated from this level to even behavioral level as such. And another way of implementation is using get level logic. You can use a primitive get, and this is how you use. And you have seen this here. So, full adder I do not have to say, sum, carry, truth table, and this is the final thing. So, here in order to implement in using get primitives, you can whatever you see as the circuit, you can straight away implement. This also has been explained earlier. So, that is what we are doing here. And note that this is an output and these two are inputs for an exclusive OR. And you can, if you want, you can say U1, which will instantiate, you can use that. And there is no need for you to put separately here. Probably I think you can put a comma and add one more U2 like that. And this is what is realized here, exclusive of 3 inputs. And then A, B, B, C, C, A, the majority logic for the output as such here. And these are all the intermediate signals S1, A1 through A3, O1 etc. here. And this have exactly the same meaning as exclusive OR. So, always output followed by the inputs AND operation for a 2 input AND operation, 2 input OR operation here, and that is what you had here. See, these are all S1, A1 through A3, O1, that is precisely the intermediate outputs that we have used. So, next we went to implementing a magnitude comparator, and this always block and with 2 numbers as such here. These 2 numbers are compared, and accordingly the outputs are set. If it is greater this, if it is equal to this, and so on. So, this code is given over here. It is plain 1-to-1 correspondence you have here. So, this is the one. You just, when it is greater, you just assign here. Braces are always easy to read. So, you make it a habit to use braces freely. And again not equal to and less or equal to, and in always block you use that one. You should distinguish the difference between that. Here it has a different meaning, right. It means precisely less or equal to. in an always block, I mean non-blocking statement it is called, that is mere equal to. So, we also consider one design example as such, and this involved computation of sum between two numbers, 8-bit numbers, only when enabled sum is energized, and compared with a preset value, and if the final sum is equal to this, you output a match signal, otherwise more or less. That is how it is here, and precisely the same thing is being done here. This is a mux again, which you have already seen, and this summation is assigned to sum, or 0 is assigned to sum, depending upon enabled sum is 1, that is active or not. If it is not active, we simply make it 0 in order to distinguish that no action has been taken there. And similarly for match, it is precisely the same thing. You just use sum equal to preset value in the select pin of the mux, so and assign in a similar fashion. So is the case for more and then less up to this, and then end. So we have come to the end of our combination circuit. So we finally not forget to put end module here, and this is the indication that we have ended here. Right. So now we will go on to the sequential circuits, exactly repeat the same thing, probably a little faster as such. So because most of them are going to be repetition, and once again we see that we have to give a name, meaningful name. Here we are going to do only sequential circuits, so we use this one, and the file that you have for this module is .v as such. That is why it comes right on the top here as .v, and .v for the Verilog extension. And here there is another new thing which we have not seen before. So there is a tick here and followed by a define. This is to define, suppose you have a variable, then you can define those variables. You have also another counterpart called parameter. We will not deal with it right now, probably we will see later on. And so you say define, and then here this indicates the state machine. Finally we will be seeing a state machine model, and in that we have used S0 through S3 for state. So we can list all this here, and while writing the code we can deal straight away with S0 and not the actual number. It is cumbersome to use a number at every point. So it is always easy to use a symbol like this, any meaningful name. That is why we can define using this directive as such, and this signifies this is 0, and this is only for our readability. This decimal is what will ultimately reside will be in binary fashion, but while we deal with it, it is easier for us to resort to a decimal as such. And once again 3 bits binary, because maximum we can have is 7, right. So I just put probably you can correct it to 2, because if it is going to be 3, 2, right. I will check it up later on, but you can straight away correct, because right now I have listed only this. In which case you might have to use a default. If you use this one, ultimately a case statement you will be using for machine state diagram, I mean a state machine, and therein you have to take care using a default. And once again sequential circuit is the module name, and we declare this is the keyword as we have seen, and declare all the IOs, list all the IOs. As I mentioned, now output is coming very close to this. So this time I have put all whatever function that we have, those function as such I have put, instead of listing all the inputs and wondering to which module it belongs, I mean which part of the code it belongs to. So it may be a good practice. If you like this, you can adapt this, right. I have shown both, and once again ABC, they are all different IOs, and there is a clock reset. Then in addition to that we have a hold pin also. It is similar to a microprocessor hold signal, and there are other IOs. We have a shift register, so we use shift in one and so on, and we have also done monoshot trigger input is required for that monoshot, and corresponding outputs, and one internal counter is also required for the same. That is what we have put here, and final output is what is called delay output, and we have already seen this in detail. That is why I am going little fast here, and anyway we will revisit when we do for simulation, and this is precisely IO listing as such for different. This is we have also done a parallel to serial converter. So, this IOs are pertaining to this right from here to this up to end of conversion. So, which part it belongs to, you can probably comment it like this, or if you require you can put more comments. And then for a state machine we had some to indicate every state, we had put a lamp there as output Z0 Z3, and that is also listed here. And we had finally a pattern detector as such, a pattern sequence detector, and its IOs are here. Both of them are 1 bits as such, and finally bracket completed and with a semicolon. So, usually people forget, especially beginners, they forget either this or no comma here or a comma there and so on. And once again you identify what are the inputs there, and as you can see I am not going to the details as such. So, you can just browse through that, and outputs here, and once again multi precision outputs and single precision outputs. Once again here multi precision and single, and you see that input has been brought again here, right? Input output, you can mix it in any fashion that you like. And after that you have to identify reg, which we have already seen here. Then you list wire and reg, and this we have already explained. Wire is an assign output, you can use wire, and always block outputs, you can use reg as such, and that is precisely what we have. So, finally it ends up in I think this is a pattern, yes, that pattern sequence detector IOs here. Now it starts the code for each of this, and if you see here, of course I do not have, it is nothing but a D flip flop which was put on the board, if you remember, and you have an always block, and with positive edge of clock or negative edge of reset, only you take the action, and you can reset the flip flops whenever a reset is applied, and this is done right at the power on stage, and there are two outputs Q and Q underscore n, which you know as a D flip flop, and you can initialize this here Q to 0 and 1 here. And then in the course of normal working of the D flip flop, you just assign whatever is in D input to Q, and inverted D to Q underscore n. But unfortunately this creates two flip flops as such when you look into the synthesis tool later on. So, way out to decrease the count, you can put this as an assign statement outside. So, and have the same result, only an inverter will be used. That may be a better approach. And here what we have, two registers we realized in this fashion, and we wanted to the actual when you have just a plain register, which is nothing but a collection of flip flops, say D flip flops, and depending upon how much bit you want, and there are reset, set controls, and clock and hold for this, and whatever it stores here, we want it to use only with the arrival of the next clock edge. So, that in other words, we want to delay one particular signal, in this case what is called a pixel out valid with a P standing for the previous value. Actually this is the real value that we are interested in, but we want it at the next clock pulse. So, what we do is we put another register and then register it there. That is what you have it here. We have already seen this before, and whatever set and reset condition are all applied here, and the corresponding code is what is shown here. So, what you see here is set pixel out and reset pixel out for ABC and A bar, B, C bar here, and then always block to realize the first register that you have here, and that is with the P pixel out P valid, and the same thing if there is a hold like a microprocessor signal, it will just write back itself, and that means to say it does nothing but just idles, it does not do anything. So long as the hold is asserted, it keeps on going in this so to say block looping here. That is how it preserves at the time of hold, and when hold is removed, it continues from where it left, it does not start from square one again. That is the beauty of using a hold. And this also we have seen if statements and else if statements to realize when a such and such condition is met, do this, otherwise do that. So, the otherwise is this, final otherwise is with an else, that will be mark the end of this entire always block with if else if notation. And here you see that once again it is saving back the same thing, because we do not want to lose its contents. And next register takes this as the input, and precisely reset etc. are same, hold etc. are same in this next register. Here that previous content is assigned here. So that means say in the earlier clock this might have matured, it was 1, let us say, that 1 cannot be assigned right at the same clock here, and so what we do is we assign it only at the next clock. That is how you get a 1 clock delay. If you want more clock delay, you can put a counter, run a counter when a particular condition is satisfied, and then when a set value is reached at the counter, then you can take the action. So you can delay as much as you want. And this is a counter realization as such. Right. In counter we have declare it as counter reg. So it is only to facilitate its register. All flip flops are basically registers, right? And it is 8-bit and MSB once again here. And you want to advance the counter, then you base it on ABC status as such. If all of them are 1, then only you advance here. That is what is applied here. And if you want to reset when the counter reaches say 255, in this case it may sound redundant because next value will be automatically 0, it will wrap around being 8 bits. But any other number you want here you can also use, that is why it has been put in a general fashion like this, right. And there must be a clock and a reset also, because all flip flops normally need a reset, power on reset as such. Okay, we haven't seen the code for this, I think. This is the code for the counter, which we have already seen, advanced counter, and counter is actually pre-incremented here by using assign statement in order to save computation time and thereby speed up the process. And here as usual with a reset, you reset the register, and if not with reset condition met, this will be met when you want to physically reset with an external reset input or with a count value, which we have already seen here. This reset condition is here, it happens to be only with counter equal to 255, only then you reset here, that is what is covered here. And if you want to increment the counter, then you have to see that ABC is 1. So that will be 1, then this will be asserted here, and that counter which was pre-incremented earlier statement will be assigned only here. you may think that is it not going beyond the time. It will not, because whatever is pre-computed here again depends upon this register only. So, it will not keep on incrementing because it is assigned in an assign statement, which is a combinational thing, right. So, it depends upon the counter edge. So, only with this will change only with the arrival of the positive edge of the clock. So, you can rest assured that this also will change only with the arrival of the subsequent to the arrival of the positive edge clock. So, we have one retriggerable non-retriggerable monoshot, and earlier it was mentioned that we needed 256 clock cycles for delay. I have subsequently I have amended it because it is easy to keep track that set value is what you really get. So, I have amended that one, although the previous code will work for 256, that has been amended, and that amended statement will appear in this case. I will tell in a minute. See, you can reset based on this condition when reset is applied as well as counter here, and this run delay is to detect 0 1 rising edge of the trigger P, which is the input to the mono here. This is based upon the counter being equal to 255, and with a trigger you start the timing action, and out comes the delay here, and this is delay out, and this is the internal counter that runs here. If you wish to use, you can use that, otherwise you can just ignore that. And now you might have noticed this is the change I have made here, right. So, also here, and that is precisely what is written here. For run delay, we sense the rising edge here, and as usual we pre-increment the register that here, and earlier I had used just CNT, I have renamed it as D, right, to indicate it is a delay that we really want to do. So, I have just renamed, because otherwise that earlier counter will be overwritten by this, or this will be overwritten by the other one. So, we can't predict that. And we have an assignment of always block which does the actual sequential work. So, that is namely the counting, and that is what is here, and with reset condition being satisfied, you reset the system. All these different counters, delay, output, and there is internal storage for trigger condition to store the previous status as such. That is what is here. And if delay, I mean timer is already running, it would have been forced to 1. So long as it is running, then only you do the incrementing. That is why this increment is here, right. And we do not forget to preserve the current trigger value as a previous value, so that we can use it in the next clock cycle and thing. And if run delay is actually the sensing of the rising edge, if it is 1, then you have to start the timer action, thereby you are making delay out as 1, right. And once again you preserve this here, and the whole thing ends there, right. This is if else you do not do anything, just preserve what you have here. We have some more circuits, say shift register, etc. I think we will cover this in your next class as such. Thank you.